All right, it's 1:05. Let's get started. Okay, my name is Sean. I'm a member at Monash DeepNeuron. I'll be your guide today. For most of you, your first intro to deep learning and actually coding something using a AI framework. So that's exciting. So let's go through some housekeeping stuff. So as usual, please mute yourself, and if you have any questions, please leave them in the chat. We have quite a few demonstrators here today. If you have technical issues, leave them in the chat. They should address them with you one-on-one. And for the quote-unquote lecture today, it's not a typical lecture that you would expect. It's definitely an interactive session, so we'll take pauses every one to two to three slides to go through any questions, and we want to make sure that everyone understands the content and doesn't get too behind. So definitely leave them in the chat. We'll go through them, and yeah, we'll learn heaps about deep learning today. Okay, so just the general structure of the workshop. So around now, we'll start the theory of deep learning. Just nothing too intense, just the basic bare bones theory that you need to understand what you're seeing in the code. And around 2 p.m., we'll start our practical. More on that later. And around 2:55, we'll all gather back to the main room for a quick summary to link our understanding of the code to our theory. Okay. All right, so what is deep learning? So the deep learning boom has been happening for the last decade or so, but AI and machine learning in general has been going on since the early, or actually mid 50s in the US. It's gone through quite a few booms and research winters where nothing was happening for a couple of years at a time, and there were booms when certain industry requirements called for it. And for the last decade or so, one of the main reasons why we were able to revitalize this field was thanks to video game nerds mainly, and NVIDIA pushing out GPUs, and these GPUs that are in our computers are very good at making these deep learning calculations. So what are some deep learning applications? And specifically for this workshop, we have a medical application context. So deep learning obviously can be used with computer vision, image recognition. So it's able to break down an image and classify things. So that's huge. As you can see here, classify different parts of the lung and whatnot, and we can train it in a whole wide range of ways. But today we'll focus on computer vision and image classification. All right, and the code that we're using today is, well, the framework we're using today is called FastAI. It's sort of a beginner framework, and it's built on top of PyTorch, which is more of a professional, more sort of like custom research environment. So people like Facebook and Tesla, they use PyTorch, but today we're using FastAI, which is built on top of PyTorch. All right, so this is a practical workshop. So the focus on this workshop is to just get through enough theories so we can understand what we're seeing in the code. So when we go through the code, definitely take your time to interact with your demonstrator and go through line by line, understand what is happening, and play around with the code. That is the aim of the workshop. Definitely, yeah. it's deep learning theory can get pretty confusing. So practice over theory. That's the goal of the workshop. Okay, and most of us here today will be using Google Colab or Collaboratory. It should come with your Google apps when you sign up for Google, but we can sort out those technical details later. But the main goal of this is it's sort of like a notebook that you can separate out your code and run things in cells. So usually when we run code, we run it in one sheet, one page, like we click execute and the whole thing just runs. But Colab breaks it down in chunks. So you can, that's really good for deep learning because you can print out images and look at them and go through details about the data set before you train the neural network. All right, any questions so far? Nope, I'll take that as a no. All right, so what are the key ingredients to making a neural network work? So we have our data set. So that has nothing to do with AI or even the model itself. Is completely, it's all about what you want to train, what you want to focus on. So in the medical field or in the medical diagnosis context, it would be perhaps a whole set of CT scans that you want to classify, and we'll look into what these terms mean. And then you have your model, which is how you're structuring the neural network, how you're connecting the layers together, and then at the end you have training, which is how you go about training the model. What are some of the problems that can occur? What are some parameters that you can put in to make it train better? And what are some attributes of the model that you want to focus on, such as losses, accuracy, and things like that? All right, so let's look at data preprocessing. So as we've said before, this is the data set portion of the neural network. So if we want to train the neural network on classifying on dogs and cats, it's obviously important that we have to begin with a stack of images that are what we want. So pictures of dogs, pictures of cats, and we can acquire them either by downloading from a site like Kaggle. Kaggle is like a deep learning research site that people can just steal data from. And yes, we want to be separating them to dogs, to a dog folder, to a cat's folder, and we want to be separating out any irrelevant images, such as maybe if you're doing web scraping, you're going on Google Images and you're just typing dogs in Google search and you're just pulling off tons of images on dogs, and maybe you get a few that are not relevant to your research. You probably want to X them out. So that's part of the, let me pull that. Yeah, that's part of the data preprocessing process. So you want to be separating out the pictures into folders, neat folders, deleting anything that is not relevant, and putting them into a folder called training and validation, but we'll go into that in the next slide. Okay, any questions so far?
We have a question in the chat, Sean. Is this related to what capture does in any way?
Pardon? Capture, what does that mean?
Okay.
Oh yeah, okay,
Jeffrey,
yeah, capture. Capture, right.
It's Google Capture.
Yeah, I forgot how to spell it. Yeah. So,
CAPTCHA would actually, for security reasons, they would actually ask you to either select pictures or decipher letters or numbers written in a very special way. And behind the scenes, we don't actually know that aside, CAPTCHA actually has two functions. One to actually basically does an obvious thing would be to protect the company's privacy. And the second thing, which is less obvious, would be to allow deep learning, to allow the computer to learn how to decipher certain scripts or pictures. So is that what they?
So what you say is correct. Sorry, Sean, am I overstepping? Are you going to answer?
Oh, no, go ahead. It's a free discussion. Yeah, go ahead.
Sure. So especially with what Google is doing, for example, in some of the captures, you'll see, say, images of a street, and you'll be expected to click on which ones contain, say, a car or a fire hydrant or a traffic light. What you're doing in that case is helping them to outsource their labor. So you're helping them to generate a data set for them to train their models on. In the case of the words, I'm not too sure there, but it could be something similar happening there. So yeah, it's not so much that it's difficult to get a neural net to do this kind of automation, but by having you outsource and do some of the work for them, they don't have to pay someone in order to generate their data set. And the way that they know whether or not you're doing it correctly or falsely is they might put in, like, say, 6 out of the 10, which has already been viewed by other people. And if you are in rough agreement with them, then they know that you're making a genuine attempt.
Right. Thank you so much, Mitchell.
As well.
All right, good question so far.
We've got another question as well, if you have a
Yep.
look in the chat.
So the question, Sean, is whether or not Python, and by extension PyTorch, is the industry standard.
Well, we have another thing called TensorFlow as well, but let's not get to that's not the point of this workshop. But yes, as I said before, Tesla uses PyTorch. People use TensorFlow as well. Yeah, so those are the two main big players for deep learning frameworks, and both of them are in Python. Yeah, yep. Okay, so let's move on. Let's talk about training and validation. So as we said before, we want to have our stack of images to begin with. That you can get that from downloading from Google or whatever from Kaggle. That's called a data set. And we want to be splitting them into generally 80-20%, where one stack or one folder would be used for training the neural net. And then once we're done with the training, we want to be obviously vetting the neural net and checking whether it's actually doing what we intended to and check our accuracy and whatnot. So we separate, we want fresh images for that process, for that vetting process. And we call that the validation set. Forget about the test set for now. Okay, so let's assume that we are working with black and white images. So this is just the same cat image that some of you might recognize. And yeah, for simplicity, we'll work with black and white images for this example. And if we break up this image and just think of it as how would the neural net think of this image? How would a computer think of this image? It would think of it as a number for each pixel between 0 to 255. So that would correspond to how dark or how bright that image, how dark or bright that pixel is. And we can call these individual pixels x1, x2, x3, x4, and so on. Right? We can label all these pixels. Is everyone okay with this so far? Okay, so yes, as we said, we want to break up our image into pixels, and we can think of them as individual inputs into the neural net. So x1, x2, xm, and these are like, you can think of them as pixels, but for us to understand it better, I made the pixel a little, like the quote unquote pixel bigger, but in reality, it would be like little bits of this cat's eye or whatever. And these are the inputs to the neural net. And then we have weights multiplying each input, and then we're summing them. So what are weights? So why are weights such a big deal? These guys here. So these weights are not determined by us. These are up to the neural net to decide what these weights are. So that's the deep learning part of deep learning, right? The neural net has to decide how important is in the goal of categorizing a cat, how important is being able to recognize this part of the image. How important is that in the output, right? Like, is it that important to know that there are these parts of the image that make up a cat? Like these pixels don't really matter, but we want to find out specific parts of this that are common to all cats. So these weights will help us in doing that. Any questions with that so far? Okay, so once we sum them, we want to put them, go away. Yep, we want to put them through a nonlinear function. Let's call it g of x, right? So that's part of the process, but let's not worry too much about that for now. Let's make that go away. Yes, and at the end, there's an output. At this node, it's going to have a prediction. The neural net's going to have a prediction. It's going to say, okay, I think it's 0.3%, 30% a cat and 70% a dog, right? So that's its prediction. And that's like the mathematical notation for it at the end. But also, let's not worry too much about that. Okay, so once we have that single perceptron, so this whole pipeline here is called a perceptron, right? From input all the way, blah, 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 all these intermediate steps to a prediction at the end. So that's one perceptron. So we can start building on top of each other, these perceptrons, and making what we call a dense layer, right? Where we can see this. So Z1 would be sort of like this step, this red arrow here, before passing on to a nonlinear function g of x, right? So before passing on to g of x, Z1 is like the red arrow here. And Z1 is made up of, instead of just one part of the image, is a combination of different parts of the image feeding into Z1. And Z2 is also has inputs from different parts of the image. And all of these blue lines have their own separate weights. So none of them have the same weights. So the neural net has to remember all of these weights here. Any questions about that so far? Okay, trucking along. Now we're going to extend this idea into a full neural network. Well, with our inputs and our outputs at the end, and some stuff in the middle, right? Some combinations of these inputs, along with some multiplying by some weights, and then maybe some more z's in the middle. And then at the end, there's some prediction at the end for a cat prediction and a dog prediction, right? Is that okay? Like it might look a little intimidating, but it's all just think of it as cats in, and then prediction out, and then some multiplying in between, and some functions in between. But yeah. All right, so for today, we're doing computer vision. So we're going to be talking about a specific type of neural net called a convolutional neural net. So there are obviously different types of neural nets, like a recurrent neural net, modular neural net, but we don't worry about these today. Let's think about convolutional neural nets. That's the specific type that we're working with today. So we have some image. Using some math black magic, we do convolution and ReLU. That's just some math stuff, and then we have that image on a thing called a feature map. So when I said before, we want the neural net to be able to recognize specific parts, or not specific, general parts of a cat. So there are a million images of a cat, but how does it understand that it's a cat? There are certain features of it that stand out, like whiskers, like the shape of the eye, maybe the fur or the color.
So there's a question about what is ReLU.
Okay, so ReLU is this. ReLU is this guy, but yeah, let's not worry about that. Probably should have. Yep.
Essentially, ReLU is a nonlinear function. If you don't have a nonlinear function in your neural network, the best you can do is a linear approximation, which means a straight line. If the curve that you're actually trying to fit is anything which isn't straight, then you're going to have a big problem. So that's why we need something like ReLU involved.
Yep. Okay, so these feature maps are parts of the cat that we want to recognize. So maybe this would be the cat eye. So this layer would just be responsible for recognizing an eye of a cat, or maybe cat fur, and so on and so on. So we can have all these features about the image that we want to classify that are general across different examples, and we want to be able to remember those. And then more nonlinear stuff that we do to it, eventually we're going to have a prediction. And this layer is the perceptron sort of architecture that we were looking at before. Sort of this action here is at the end giving us the output. Okay, is that all right so far?
So it seems like it's getting broken down into like smaller pieces, but like more of the smaller pieces. Is that generally what's happening?
Yes, that is right.
So, correct me if I'm wrong, Sean. They usually start with the first layer is like the really basic like outlines of shapes, and then as it goes through the different layers, it starts to construct more and more complex features. So, like let's say if you were doing you were trying to recognize a face, it would start off with lines, sharp lines, and then by the second layer, it might start to recognize like eyebrows and certain features, and then by the end, it will hopefully construct an entire face. If that kind of makes more sense.
And I suppose at the end, like let's say if you're looking at like the face of a cat compared to the face.
It just cut out.
Sorry, so I suppose if this was comparing a cat to a dog, the face of a cat compared to the face of a dog, the different features between the two, you would have like a big list of them, and then I guess through the weights, it would give you the different values at the end, like the 0.3 or the 0.7 that we saw before. Is that sort of cool?
Yeah. So,
To give an example, perhaps it learns over time to recognize something like whiskers. If it recognizes whiskers to be present in the image, then the chance of it predicting cat goes up. But it still has to predict whether or not there is whiskers there, whether it's a cat or a dog, which is why we need these, many features at the end, right? So you want to be recognizing many different kinds of complex features.
Yeah. And I think like the first few layers, whether or not you were determining between a cat or a dog would actually be pretty similar, which we'll go into a little bit later. So yeah, it would be like, both cats and dogs, have eyes, and kind of a general like four-legged animal kind of thing. But later on it would start to distinguish in the later layers between like whiskers and anyway.
Gotcha. Thank you.
Yeah, so great leading into my next point. So exactly as we said, so we want to be extracting features. So you can think of features as parts of a cat, so cat whiskers, so that would be a high level feature. So what does that mean? So in order for a neural net to understand what a whisker is, it's going to understand what an edge is. So it's going to know, okay, that's straight line, that's an edge. Okay, edge, good. So what's even lower than that? Like it just keeps going down. Like what are like the most basic shapes of a part of a feature that we can break down to, and these features would be picked up by different parts of the feature map. So as you can see here, some of the visualization. So that looks like a honeycomb or some sort. So in order for it to understand what a honeycomb is, it's got to understand shapes. And in order for it to understand shapes, it's got to understand edges. So you can abstract down all the way to the lowest level. So that's how it builds up from just a corner of an image all the way to all these complex shapes that you see here.
So Sean, what's the fully connected part for?
Yes.
Like so you've like created these, yeah. Sorry, you go on.
Yeah. So the convolution part, this part, convolutionary part, is just responsible for image classification, or well, in this case, just image classification. It's just responsible for picking up these features. But in a neural network, we're not always going to be working with images. So in our specific case, we're dealing with images. So we have a convolutionary part, and then we have a fully connected part. Fully connected parts can be applicable to just about anything, right? We can be working with languages that has nothing to do with images, or picking up features, but we still need a fully connected part. So that's how connecting these two ideas sort of work. So the fully connected part is the perceptron idea that we were exploring before.
So the CNN extracts the information and the fully connected layer makes the decisions. Is that what you're saying?
Yep. So the CNN would be before this prediction part, and its job is just to purely pick up the features. It doesn't care about the predictions. It doesn't care. Yeah, it doesn't. That's not relevant to it. All it cares about is some input, and then breaking up that image into features that we like. Any other questions?
Yep. So we've got a question here. So someone's asked, more layers you have, the more accurate the prediction.
Well, so that question is more geared towards advanced design. So it's not necessarily true, but generally, yes. And also there are other trade-offs that come with more layers. Because as you can probably guess, the more layers you have, the more weights you have. And the more weights you have, the more numbers that the neural net has to decide on. So there's a trade-off there. But this workshop isn't about deep learning engineering on that level. So yeah, I'll just cover that question at that level. Anything else? Okay. Now, what is this thing that you're looking at? Looks kind of weird, but when we have a prediction, we're going to have some sort of error, right? Predict, so we have y hat. As we remember, it thinks 30% is a cat, 70% is a dog. So obviously, if we're passing an image of a cat, it should be, we want it to be 100% a cat and 0% a dog. So there's a pretty large error there, right? So this error, this difference here, is how the neural network learns, much like how we learn in real life, right? Like since we're all students here, if we sit a practice exam, and after we finish it without looking at the solutions, and we look at the solutions at the end, we're going to see some differences, right? And in learning from the differences is how we learn, right? So this is like a similar process here. So there's going to be some loss, right? Don't worry about the specific numbers, but there's going to be some loss, some difference between what our goal is and what the prediction is. And once we have this loss, we call it J, and it's a function of weight, all the weights that we had before, blah, blah, blah. This is just a function of two weights, but obviously, even in the most trivial models, we're going to have more weights than that. I see some questions blowing up, so let's address those before we go on.
They're actually answers, don't worry about it, Sean.
Okay, cool. Yes, so we have a function J equals referring to the loss. And we want to take some derivative. Why do you want to take a derivative? Why do we care about derivatives? Because we want to move to the lowest loss. So if you think of this, so these points are like high loss, right? Like this is like J equals 2. That's like pretty bad, right? That's like a maxima. We don't want that. We want like a really low loss. So we want to be able to make our way as a function of the weights down to the lowest point that we can get. So we want minimal loss, basically. So in the practice exam analogy, when we finish the practice exam, we have very little errors from the actual solution. Right. So how do we take this path? So we take a gradient. So that would be, in the single variable case, just dj dw, right? But in this case, it will be, taking derivatives. That's a del operator and j, and then blah blah blah, some derivatives, and then we want to be able to adjust the weights. Hang on, actually, a better way to do this would be to go back. Yes, so if we make some prediction here and we get the loss, we want to be able to go back in time and fix up these weights, because these weights are what caused this bad output, or this output with errors to occur. So we want to use the knowledge that we gain from taking this derivative and go back in time and fix up these weights, change the weights. And again, we don't decide on these weights. Not humans don't decide on these weights. The almighty neural net decides on that. So it's going to decide on some new weights here, new weights. And then the process repeats itself. New input come in, and based on these new weights, we're going to have a new output.
To put
Any
that
questions?
into a less mathematical way, when you calculate the gradient, essentially what you're doing is you are working out which way you need to update the weights in your model in order to improve your loss. Remember, loss is a function for how off your prediction actually was. So by calculating this gradient, we are working out how to better improve our model so that we get more accurate results.
Is the gradient between different, so like let's say you have one image and you find out the loss value of one image, and then you find out the next image. Is the loss the difference between, is the gradient the difference between the losses in the analysis of each different image?
I believe it's the difference between each image and what it is labeled to be. So
So the loss is the difference between what it is and what it predicted.
Mm-hmm.
The gradient is the information for how the weights actually have to change. So for example, maybe the weight is currently at, I don't know, 0.9, so some number. And the gradient says you need to move downwards to some smaller number. When you're actually running the code, this is all abstracted away. You do not need to worry about this. But essentially the gradient is informing the weights how to better predict.
Yeah, it's just that, so if you're trying to get a gradient, you need some sort of like actual, I guess, like function, or you might need 2 points. I guess you're just doing like some sort of like linear interpolation.
Yep. So if you imagine every weight as being a dimension, you now have a thousands of dimensions graph sort of thing that you're working with. And that there is going to be therefore some solution to the gradient, which will bring the loss to some minimum.
Okay.
That's very difficult to actually put on a graph.
Yes. Yeah, I could imagine. Yeah.
So we've simplified it down as like this three-dimensional thing, but that never happens in real life. In reality, you're dealing with hundreds of dimensions.
Sure. So is that done for every single image that you feed in to train it?
Yes and no. You do it in batches.
Okay.
So you calculate it for each image, and then you bundle it all up together. So
Okay.
you get an average, right? Because if you move for every single image, then it can be quite noisy.
Thank you.
Okay, good. Anything else? Okay, cool. All right, let's look at how a training run would go. So you would get from your training folder an image, might be a CT scan, might be an image of a cat. Pass that on to the neural network. Inputs. Through its weights, there's going to be some intermediate steps. You get a prediction. You get a loss. From the loss, calculate your gradient, adjust the weights, maybe show your accuracy if you want to see how you're going. So that's one training run. And after the training run, there will be new weights, as we discussed. And now validation comes in. We want to be able to see how these new weights are actually behaving. Have they updated in the right direction? Because sometimes the algorithm can go really wrong and not update in the right direction. And we want to be able to see that, since humans are not micromanaging those numbers per se. So we get our validation folder. We get another picture that is relevant to our predictions, pass that on. And these new weights will inform a new output. And we're going to get some validation accuracy. And we call that whole cycle an epoch. So that's one epoch.
So there's a question about, can a network correct itself if it goes down a wrong path?
So it doesn't work magic. So it's as we said, there's a specific way of how it does things, namely this, most of the time. So if, as some of you might have learned multivariable calculus, or let's not even bring it into calculus. So if it keeps going down a path and somehow it thinks that this path is better than this path, like somehow if it comes down to this foot of the mountain and it thinks and it does a gradient calculation, and somehow for whatever reason, maybe there's a really ugly cat in the data set, it thinks, all right, maybe we should go this way. Then it just keeps trucking along this way, and then never to be seen. This global minima will never be seen again. So that's what we mean by going wrong, quote unquote. Like the loss never really goes as low as we want it to. So yeah, that's a problem there.
So Sean, I'm a little bit confused by that. Shouldn't it always take the path, the steepest gradient, no matter what? And I guess the point of it taking the wrong path would be that it ends up at a local minimum, not a maximum, rather than it would always follow the same route given the same gradient descent map or loss map, sorry. But it might end up like in a local min.
Right. So what you're saying that it's definitely not. Okay, let's all use the word deterministic. So what is the loss dependent on? It's dependent on its weights. So each time it goes through the run, there might be different way. There might be a different image in the batch that might, or in the folder that might change the way the weights are on each run. So you're not going to get the same exact weights each time, right? So the weights are going to change. So if the weights are changing each time and not the same, then the losses are going to be different. If the losses are different, then the gradient path might be different. So that's how you end up going somewhere else. But it's not as random as that, but there's a chance that it might. And also it depends on how large of a step we take. So that's a step. We can go. Yeah, we're going to cover that later, but might as well now. It's if we take a big step, that's going to change. So if we're here at the foot of the mountain, if the human told the neural net, let's take a big step each time we update. the big step might lead it really wrong, or it might really lead it to the right place. So that's called a learning rate, but we're going to cover that in pretty soon. Anything else? Okay. All right, now let's put it together. So we have the training, get the output, validation, blah, and then that's one epoch, right? And we can just keep repeating this. Just keep going and just have multiple epochs. And each time the epochs goes through, there's going to be hopefully better and better weights. So each epoch, there's going to be new weights that improves, that based on the gradient, it's going to minimize our loss. And if we minimize our loss, this output is going to be better and better. That's the idea. That's how it learns. So given enough epochs, hopefully by the end of the training, or by the end of this whole process, there's going to be a neural net that has the appropriate weights to classify this guy. Oh. Okay, so visualizing our errors. So it's pretty important in deep learning in general for the human to look into what it's actually doing. So in this case, in this specific example, we want to be looking at the losses. So this is so one way of doing that, especially in FastAI, is plotting a confusion matrix. So at the end of your training run, you can evaluate a model by looking at, all right, what's the probability of us predicting a cat and of it actually being a cat? So in this case, is 92%. What's the percentage of us predicting a dog and of it actually being a dog? And then these numbers are like what we want to eliminate, because that's when it predicts a dog, but it actually is a cat. So that's bad. And don't worry about the columns not summing to 1, because I actually borrowed this image from another matrix. And yes, we'll have top losses as well, but we'll look at that in the code. Yeah, so don't worry about this too much for now. Any questions? Okay. Oh, we have something.
So the question is why we have validation set.
Yeah, so yeah, it's important to, in a way, having a validation set is good to tell you that, all right, we should probably stop training now because these things are happening. So the accuracy is going up high enough. We should probably stop. So there's a reason why we don't want to keep going through multiple epochs. It's called overtraining, but I wasn't going to cover that in this PowerPoint. But yeah, since we're here, so yeah, it's important for us to print out validations and losses so we can see how the model is doing on each epoch. And yes, accuracy going up is good, but if the loss is also going up, then we have a thing called overtraining. So if we go back to the practice exam analogy, that would be like doing the same practice paper over and over again. So maybe by your 10th time of doing it, you're going to have a really low loss. You're going to make very little mistakes. But does that mean you actually understand a unit? Maybe, maybe not. maybe you just did a really good job of memorizing the specific questions that are coming in. So in this case, in the neural net's case, the neural net just got really good at memorizing these specific images of cats that we're putting it that we're giving it. If we were to pull a random image of a cat, maybe I'll just take a new image of a cat of my cat today, and I just put it into the neural net. That's never been on the internet before. It's going to do really badly because it's all of the weights are specifically tailored to that specific set of data. So it's important that we have a validation set to just know where we're headed. Yeah. Is that clear? Okay, so we're moving on. All right, so we have our architecture of the neural net here. So we want to be, well, we can be stacking more layers on, right? Like what's stopping us from doing that? Why not just stack more, right? If we want more weights, we can just stack more weights, right? No worries there. And that can just keep going. Right? We can just have our inputs and we can have an arbitrarily deep or long neural net, and it can go on for as much as we want, right? And that can get pretty complicated. That's going to be a lot of freaking weights that we have to train, right? And it's going to be quite complicated to design such a big neural net anyway. So we're going to basically steal work from people that have already done it. So we just go on the net and just basically download a neural net that's already pre-trained, or it can be pre-trained and pre-built for us. So we just abstract out this whole part, forget about it, and we have all the right weights for the. So, okay, so let's explain it better. So ResNet 18 that we're using is pre-trained CNN that has all the lower weights. So not the lower weights, the lower features like edges and lines and shapes already pre-trained, and they're pretty solid. So if we want to predict cats or airplanes or ships or whatever, we don't really have to train the edges and shapes again. Some other guy has already done that for us. So we can just import it from the net, from the internet. And all we have to worry about is training the last layer, which is part of the ResNet, but let's not worry about that as well. So all we have to worry about is training this last layer that does the prediction for us, right? So that's transfer learning. Any questions on that?
May I give another analogy, Sean?
Yeah.
Okay, so essentially, right, ResNet is trained on a data set called ImageNet. ImageNet is full of lots of different kinds of images. So essentially, we're taking an AI which has an idea of how to recognize different images. That is better than starting from completely random, right? So now we only need to teach it specifically how to get good at recognizing cats and dogs, rather than needing to teach it how to recognize what a line is. So it reduces the amount of data that we need. It's less effort.
Cool. Hopefully that, well, if you have questions, please bring up now. Yeah.
So what is ResNet pre-trained to do? Is it just to pick up random objects?
It's pre-trained on ImageNet, which has 1,000 different types of images.
Yeah. Cool.
Okay, many of you would be probably asking, what the heck is ImageNet and what am I hearing? Oh, okay, actually it's 2 p.m. Let's not go there. We should be ending now. Yeah, so ImageNet is just basically a huge compilation of images. You can look it up later if you like, if you're curious. Okay, so I'm going to be giving a quick demo of Collab. So just a quick tutorial on just the basics, and then we're going to head out to breakout rooms. And also, yeah, please pay attention to that because things can go wrong if you don't listen. All right, so soon you're going to get a bit.ly link to this file, this Collab file. And the most important thing, repeat to yourself quietly or loudly if you're on mute, make a separate copy for yourself before running these cells. Make a separate copy for yourself before running these cells. Cool? So you go File, Save a copy in Drive. That means that this file that's accessible to everyone will now be in your Google Drive, your own private one. Okay? And just the basics of how Collab works. You have okay, let's go. So you have cells. So normally code will be in one continuous file. So all of these code will be in one sheet, right? But in Collab or Jupyter Notebook, you have these cells that you can run the code and just have a look at what it's doing. So you can click play, or you can click, you can go Shift Enter on your keyboard, and it will run this cell, and you can look at the outputs of this cell if you're printing outputs, as you can see here. And you can just use that as like a playground to mess around with things without having to, each time you make a change, do the whole, run the whole sheet again, right? The usefulness of that will be pretty apparent in a while. Okay, and another short thing to notice is runtime. So in Collab, we're borrowing computers from Google. So there's CPU that we can borrow CPUs from Google, or we can borrow GPUs. So at the start of the workshop, you might remember that GPUs are pretty good for deep learning. So let's just go on runtime, change runtime type, and just save as GPU. That would improve your training time by quite a bit. And yeah, so we're going to head off to breakout rooms now. And I think we're going to share the bit.ly link in chat. There you go. So everyone click on that link. Should land you to this page and make a separate copy for yourself. And if you have any technical issues, we'll bring them up to your demonstrator in the breakout room. Don't bring them to me because I don't want to talk to you. And yeah, that's it. So be gone now. All right, so let's do a quick summary of what we learned. So here's how the first section is all about data preprocessing. So that's like the first part of the presentation that I did. It's all about getting your data set and doing some stuff to it. So in this case, we're doing some transforms. So that's like a new idea that we didn't cover in the slides. But the idea is we don't want the neural net to hard memorize the data set. So each time we pass it through, we apply some transform, some Photoshops to it to make it fresh each time, right? And then we call the data set data bunch, and all of these cells are important because for the human, we want to be able to see what it's actually doing. So in this case, we're actually seeing that the training set is around 80% and the validation set is actually around 20%. And the labels are what we intended it to be. And this part is also important. We actually want to look inside the data set and have a look at what the transforms are actually doing. So we see, yep, some images are getting zoomed in, some are getting warped, some are getting flipped. Some are sort of dodgy, and maybe better data cleaning is in order, such as this one. Maybe it's sort of weird, but I've seen some labeled clean images with purple dots in them. So that's also another issue that a deep learning engineer should consider. We have transfer learning. Using ResNet 18. And obviously, you can go on the FastAI model site and just replace this with any model CNN models that you like. And we did some training and we had to interrupt because, yeah, obviously it takes too long for it to run the whole 10 cycles. And yes, saving the weights, because we take a lot of time training. We want to basically make a save file in a game. We want to save our weights, so that's important to save. We can always load them in the future. That's the whole point of saving it. There are myriad of ways of visualizing our losses, our errors. There's plot top losses, giving us a heat map of which pixels the neural net thinks it's one instead of the other. We have learning rate finders. That's one of many ways to optimize and find the best learning rate. So learning rates are hyperparameters, which means it's a parameter that deep learning engineers have to choose. We have to tell the neural net what to do for that. And sometimes plotting it and finding the best range using slice is the way to go, but there are a ton of ways. And the point of this last few slides is to show that, yep, if we choose a better hyperparameter, we're going to get better performance. For example, 95% versus 85, 92, etc. Yeah, and any final questions? I think that's it for this workshop.
Yeah.
Someone's asking about what's happening next week. Mitchell, did you want to talk about a little bit about what's coming next week?
Sure. Okay, so I'll be taking next week, or at least part of it. We're also going to have a contribution from MYMI. I can't remember exactly who's doing that, but they'll be talking about human-centered design.
Darren from MYMI, yeah.
There you go. So Darren from MYMI is going to be covering a little bit on human-centered design. I'm going to be talking a bit about how to put your models, now that you've learned how to train them, into a service for production. So the case study we'll be looking at is a web server, but if you don't have any web development background, don't worry about that, because it's not actually the part that we're going to be looking at. But I'll be teaching you how to take the model that you've done and put it into something that to black box it away so that you can just evaluate it and plug that into, for example, a web server, or I don't know, a mobile app or something. As long as it runs Python, you'll be fine. So that's what we'll be looking at next week, putting models into production. Any questions?
I think if there's no other questions, you guys are all free to go. Hopefully you guys had a good time, and if you have any other questions, feel free to let us know.